In this presentation, I'll be discussing research that investigates how the haptic perceptual system supports perception of self-motion. Self-motion concerns the ability to perceive how the body is moving relative to the environment during locomotion. My colleagues and I have investigated the ability of the haptic perceptual system to perceive self-motion during locomotion. To do this, we've studied a simple homing task that participants perform while blindfolded. Here we have the design of a specific experiment. In this experiment, the participant travels outbound using either a walk gait or a gallop walk gait pattern. They then walk inbound and stop walking when they perceive that they have walked a distance that matches what they experienced during their outbound travel, and that has returned them to where they started out from. Here we see a gallop walk gait pattern. It involves stepping out with one leg, bringing the feet together, and then stepping out with the same leg. Here we see the results of this experiment. We can see that the distances produced by participants, as they attempt to walk back to where they started, depended upon the outbound distance and the outbound gait. When the participants travelled outbound with a gallop walk gait, they stopped short when they made their inbound reports. They underestimated the outbound distance. Said differently, gallop walking led participants to perceive that they were travelling through the environment more slowly. One way to interpret these results is to conclude that the manipulation of outbound gait to be a gallop walk or a walk led participants to perceptually measure their movement through the environment in different ways. Put simply, we're proposing that there are two different types of perceptual measurement for haptically perceiving self-motion. A prediction that follows from this idea that there's two distinct types of haptic perceptual measurement is that we should see other gaits producing homing task results that are either similar to gallop walking or that are similar to walking. Consistent with this prediction, here we see data for the hesitation walking gait pattern. We see that homing task performances look similar for gallop walking and hesitation walking, and that we see that both of them look similarly different from walking. Next we have a two-legged hopping gait pattern. We find that when participants locomote using a two-legged hop, they perceive self-motion in a way that's very different from walking, but that's quite similar to gallop walking and hesitation walking. What we're seeing here then is that gallop walking, hesitation walking and two-legged hopping all appear to measure self-motion in a similar way, in that they're all similarly different to walking. Another prediction that follows from the idea that there's two types of measurement for haptically perceiving self-motion is that when two gaits of the same type are used in the inbound and outbound phases of the homing task, we should not see systematic patterns of overestimation or underestimation. Here we see the results of three experiments, in which the outbound and inbound gaits were of similar type. Unlike before, we do not see a systematic underestimation. A glaring question that arises here is, why does a particular gait pattern implicate a particular type of haptic perceptual measurement? A recent theory that aims to explain this is the spatial reference frame theory. This theory is motivated by evidence that the haptic perceptual system can detect higher-order kinematic variables. This theory proposes that these higher-order kinematic variables provide a basis for detecting information about self-motion. The issue now is, what are these higher-order kinematic variables of self-motion perception, and how are they selected? This theory proposes that different gait patterns implicate different spatial measurement frames. For example, it proposes that a walking gait establishes a propriospecific measurement frame, such that information about how the body is moving relative to the environment is perceived via kinematic variables that measure how one limb is moving relative to another. The theory proposes that a propriospecific measurement frame is established when either a walk, run, or backwards walking gait is employed. For other gaits, such as hopping, gallop walking, and gallop running, a proextrospecific measurement frame is established, such that information about self-motion is perceived via kinematic variables measuring how the limbs are moving relative to the ground surface. The idea here is that these kinematic reference frames select or stabilize particular higher-order kinematic variables. We've recently tested an intriguing prediction of the spatial reference frame theory. We hypothesized that if the information for perceiving self-motion is kinematic in nature, then the capacity for haptically perceiving self-motion may share its basis for the capacity for visually perceiving another person's movements, based upon seeing their limb kinematics. As we have seen, to study haptically perceived self-motion, we had blindfolded participants perform an overground homing task. Now, in order to study visually perceived motion of another person, we had participants perform a homing task by having them watch videos of limb kinematics. Participants watched an actor on the screen travel outbound, using a particular outbound gait. They then watched the actor travel inbound, and their task was to press the report button when they perceived that the actor had returned to where they were at the start of the outbound phase. Here we have the results for the haptically perceived self-motion experiment, where gallop walk and walk were the outbound gaits. Here we have the results for the replication of this experiment as a perception of another person's motion experiment. You can see that we have the same pattern of results across the two different types of experiments. Next, here we have the results for the haptically perceived self-motion experiment, where hesitation walk and gallop walk were the outbound gaits. And here we have the results for the replication of this experiment as a perception of another person's motion experiment. Again, you can see that we have the same pattern of results across these two types of experiment. Here we have the results for the haptically perceived self-motion experiment, where walk and jog were the outbound gaits. And here we have the results from the replication of this experiment as a perception of another person's motion task. And again, you can see that we have the same pattern of results across experiments. To sum up, we see some interesting evidence here suggesting that higher-order kinematic variables are involved in haptically perceived self-motion and in visually perceiving the motions of other people based upon watching the movements of their limbs. I would like to acknowledge the support of colleagues at the University of Cincinnati, the University of Nebraska at Omaha, and at UConn, and I look forward to your questions at the conference.